All right, so we are moving on to like we're talking about the 3D things. So today we're going to talk about how like we're moving to the setting where we have multiple camera and looking at one object, one scene, and want to be able to recover where the camera is and where the points are. Okay, so we're going to be able to do the reconstruct the 3D environment. Okay, so the basics behind that, we already talked about since last time, that there's some fundamental geometry relationship between two images that capture from different positions, okay? And so that relationship, it's kind of, there's no deep learning involved, so it's always true. So it's something, it's one of the fundamental things in 3D computer vision. So even though you are going to use any of the deep learning networks and kind of fancy machine learning to learn this, this will always be true. Okay, so we talk about that there's a relationship between the representations. If you have 3D point X and that's being represented in the left camera XL, and the same 3D representation in the right expressed in the right camera, they can be expressed like this, right? There's always this relationship here. So the way you can express this is that every point, key points from image one from the left camera can be, the correspondence must be in the second camera, okay? So the way you can look at this is that this guy, if you multiply this guy, it becomes a line equation from the second one. And if you multiply this guy, it becomes a line equation in the first image, okay? So this is a mathematical relationship that can describe this so-called epipolar constraint, okay? So the correspondence must lie on a line. All right, so, but here, this XL and XR, these are 3D point positions, 3D point representations expressed in different coordinate system. But what we want is that what we only have is the 2D point, right? 2D position. We can, those are the position we can actually measure. We don't have the depths. So if we express in this way, if you take the E out, kind of express, if you express this XY 3D position in the camera coordinate system, express this as this way, then you have this representation. Okay, so it looks like this. So you have a 2D point from left camera and a 2D point, the correspondence of that 2D point from the right camera. So these 2 points are correspond, then they must satisfy these equations. Okay, so this is called fundamental matrix. So sometimes what we want is that we want to be able to, the first step is that we want to be able to recover the fundamental matrix from two images. Okay, and we talked about this last time. Like the way you can do this is to kind of take seed features and do the feature matching that we talked about in module 2. And once we have those matches, you can do RANSAC to recover that. All right. So usually this involves several steps to really recover the relative positions, the translation and the rotation between these two cameras. So basically the way you do this is that you solve for the F, the fundamental matrix, that's this 3x3 matrix. And then you can, with the intrinsic, you can recover the essential matrix, and then you can get the translation and rotation. Okay, so any pair of images is, if you are able to recover the fundamental matrix as a first step, you are able to figure out what is the translation and what is the relative rotation between these two cameras. Okay, so this will be useful for any of the 3D reconstruction pipeline. Okay, so today if you go kind of capture some images and upload to some cloud or some 3D reconstruction software to recover the camera position and the 3D point cloud, it's the fundamentals is this. Okay, so they need to estimate the key points, figure out the relative position and translation. Okay. All right. So last time we talked about that we want to be able to solve for this correspondence, right? And usually, well, the way we do this is to use something called 8-point algorithms. So we have been using the same methodology over and over again, right? So in this case, the thing is that you have an equation, you have a constraint that involves something that's unknown, that's f, the numbers in the entries in the F matrix is unknown. And therefore, what you do is that you take the correspondence you have and then you expand it and move the unknown variables into a column vectors so that you can use your linear algebra tools, either solving this with least square or solve this with SVD. Okay. So in this case, every pair of correspondence will give you one equation, okay? It will give you one equation. And because this F, it has 9 numbers. So you may think that you need 9 equations to solve it. But the problem, a property that allows you to only need a equation is that if you look at this equation, if F is a solution, so is 2f, so is 3f. Like any scalar multiplied by f is still a solution to this equation. So which means that your f is up to scale. You don't need the last, you only, even though you have 9 numbers, there's 1 degree of freedom is you don't need to fix that. Okay, so which means that you only need 8 degrees of freedom, which means that you only need 8 equations. So that's why it's called 8-point algorithm. Okay, so to solve for these 9 numbers, you only need 8 equations. All right, any questions so far? All right, so once we set up this linear system equation, so you can see that all these numbers are kind of xy location, right? Xy location from the left image, xy location on the right image. Then you can solve for this using SVD. Right? So now you get with F, you get something that's 3 by 3, but that metric itself is still not satisfy the constraint, right? We know that fundamental matrix is it has the determinant of the fundamental matrix is 0, which means that the least singular value must be 0. So what you can do is to apply SVD again to enforce the rank of that the matrix is 2. So on the left hand side, you can see that if you don't enforce that rank, that the epipole don't converge on the center, right? If you enforce that, it will be behave physically correct. All right, and so this is how you can do it. You first solve for the SVD, set up the linear system equation, solve for SVD, and then run the SVD again to enforce that the least eigenvalue is kind of set that to 0, and then you get and then you construct the like multiply the USV to reconstruct the F back. Right. So this will guarantee that your F is as close to the original fundamental matrix estimation you have. At the same time, it enforce that the least singular value is 0. Okay, so these are kind of, we talked about that last time. All right, so, and the way you can, so this algorithm works if all the A pair correspondence, like you have a pair of correspondence, if all A pairs are correct, then you can solve for this. The problem is that you don't know which A pairs are the inliers, and therefore you need to run a RANSAC to deal with that. So the process is very, very similar to the image stitching process. Basically, you start with a list of correspondence. Some of them are correct, some of them are not correct. So the way you do this is that you randomly sample A pairs and use that A pairs to solve for the fundamental matrix, and then use the fundamental matrix to check all the other pairs to see how many of the pairs agree with my fundamental matrix estimations, right? So that's one run. and you repeat this for many rounds, maybe 500 trials, and you pick the one trial that has the most number of inliers. Okay, so that's basically, and you have done that in the homework 3 for image, like image stitching, right? So when you have this outlier, so this is a kind of very common procedure for you to get something that's robust, despite the fact that you could have many outliers. All right. Questions so far? So this is just a quick overview of what we talked about last time. Okay. If not, then once we then we move on to the problem of depth. Okay. So once we have this relative position between the two cameras, right? So given two images, then we run this fundamental matrix. We figure out relative rotation and translations. Then we want to be able to estimate depths. Okay, so let's think about a simple case first. The depth estimation. If I have a perfectly parallel case, right? I have a depth camera, so you can see that many of the cell phone has, I mean, not just two, it's actually three, right? But the top and this guy, these two lenses are mainly used for computing in stereo. Okay, so you can see that they have a disparity. They are shifted horizontally, but their orientation are the same. Okay, it looks like this, right? You have one camera on the left, one camera on the right. Okay, and you have a focal length, and this is called the baseline. All right. So if you look at one point in the 3D space, you want to determine how far that point is. You can write that from something called similar triangles, right? So where is the similar triangle? It's the distance between the baseline. Basically, there's a disparity. This x and this guy, this distance to the baseline. You can see about these are the, so where is that triangle? Okay, is this f and z, the ratio between this f and, let me see if it's, okay. Ideally, it should start with this, the disparity, that is the projection position between this left camera and the right camera. That's called the disparity. That's basically kind of, if you think about this, if you move your thumb inside your in front of you, and if you close one eye alternatively, then you'll find that there's some shift, right? There's some shift, and that shift is coming from the fact that the same thing, the same CD point, is getting projected onto different location of your camera. In this case, your camera is your eye, and that shift is called disparity. So the ratio from the similar triangle, you get this ratio, and which means that you can recover this. Okay, so the disparity is this guy, and which means that you can recover this z is inverse to the like, if you move this z to the left hand side, disparity to these things, it means that if the observation you have has large disparity, it means that it's closer to you, right? Something is further. If you look at something like fixating on something further, and you close your eyes and look at that, it will basically say like doesn't have any disparity, because as for things is very far. Okay. All right. So it's inverse to the depth is inverse to the disparity. The interesting thing is that you can measure the disparity if you find a correspondence, right? If I have a 3D point I am interested in, I find that 3D point in the image 1, and I find the same 3D point in image 2. If I know I have the 2D coordinate for image 1 and 2D coordinate for image 2, and I just computed the difference between them, then I have the depth, right? The depth is just this depth c is just the baseline times the f times the focal length divided by the disparity. Then I get a measurement of the depth. Okay. So that's kind of fundamental principle of this. All right. So where does that fundamental metrics come from? Like useful here? They are useful because it's like when I try to compute depth from two images, but those two images may not be parallel to start with. Like this is a simple case, parallel case, right? So the actual case could be something like this, right? I have two images, but they are captured on a kind of random locations. I capture the image here, and maybe I capture the same image here. Right? But how do I still be able to estimate the depth here? So the idea is that you know how to estimate depth when the images are parallel to each other. Okay, we know how to do that. So now if the thing is not parallel to each other, what we need to do is to make them parallel to each other. Then I know how to do it. Okay, does it make sense? So I know how to estimate depth by but if I have the this thing parallel to each other. All right. So in this case, basically there's a method that can this is called stereo image rectification. Okay. So the main idea is that you take this you estimate the fundamental metrics. Once you have the fundamental metrics, you have the relative position, rotation, and translation. And from there, you are able to figure out homography because image planes are, you can warp any image plane from the other image plane using homography. So you can warp this homography onto this so that it becomes frontal parallel. Okay? So there's a particular paper to doing that. I don't want to go into too much detail here. But here's the kind of the effects of this, right? When you have a on the top row, you have the images that are not parallel to each other, and therefore the epipolar lines they are not they could be oriented in different way. But if you rectify it, basically you kind of transform that one image and the second image in this way. What you can find is that now the horizontal line is parallel to each other, which means that you become much easier to find the correspondence. Previously, we said that if I have a 2D position in the image one, and I know the corresponding point must be on a line on image two, right? That is where the epipolar constraint comes in. And if the images are parallel to each other, like there's no rotations between them, then that line, the epipolar line, becomes horizontal scan line. Okay, which means that when I try to find a matching from image one to try to find a corresponding point on image two, I know there lies on a line, and in this case, the line is just scan line, like the x, where the you only need to search this direction. So it's much simpler, right? That's where the stereo comes in. You only need to, for this point, you just need you only know your candidate is going to be on the same y coordinate. You only need to scan the x coordinate. Okay, so you don't need to have arbitrary lines to search for. All right, so this makes things much easier to work with. Okay, does it make sense? So that's why that's the relationship of why we want to compute fundamental metrics so that we can warp them into parallel lines and parallel images. And because of its parallel images, the epipolar lines become parallel. Okay, become just a scan line. Okay. All right, so the algorithm looks like this. So basically, we look at an image patch. I want to determine. So by the way, this is the actual kind of historical photo where, like, back in the day, we already have stereo cameras. We kind of look at capture this photo and catch it in two photos. And with that, you actually can take one patch on the left-hand side and want to determine the depth of this patch. And what we do is that we go to the other image, read the patch coordinates of the left image, that's the yellow box, and then let's say the y coordinate is maybe 250. Then you go to the line, you draw a line on the right image, and then at the position 250, but you scan, you don't know where they are horizontally, okay? Right, and that you just check, is this a good match? Is this a good match? Is this a good match? And then you just go over that. Then you can determine what is the best location. Okay? Does it make sense? So that's how you can, once you figure out the best location, you can estimate the depth, right? The depth is just the focal length times the baseline of the image times this the disparity. Okay? All right. So can anyone tell me, how do I measure similarity between two patches? Right? Any ideas? So this is the concept of template matching, right? I have a template on the left-hand side, and then what will be the kind of reasonable way I can find the correspondence on the right image? But here, when I try to find the right image, I don't need to have two for loops to scan all the possible location. Like in the previous case, when we find the template patching, we need to find all the locations. But here, because of the stereo constraint, we only need to find on a long one scan line, like basically just one for loop. But how do we, can you think about how we can kind of measure the similarity? Basically, two patches comes in, it give me a score. Yes. Cross correlation, yeah. No, or you can cross correlation is just the image kind of intensity directly, right? But I guess what you want to say is the normalized cross correlation, right? So, okay, yeah. So one way is to do SSD, sum of square distance. Basically, what you did is that you look at let's say 5x5 patch, and the 5x5 patch is 25 numbers. And again, for every candidate position, you have 25 numbers. You just compute the difference and square it, sum them up. That is a SSD. Okay. So what you do is the following. So for all the possible candidates, candidate disparity, then you will find the one with the minimum. Okay. So you'll find like something like this. Okay. You scan through all the possible directions, and you'll find that you have some profile. But for every disparity, every different location, you have some profile and something that some profile, some particular point that is a minimum. Okay, and that will be your estimate of the that'll be your estimate of the depth. Right, this is the disparity, and if you know the disparity, and if you know the focal length and so on, focal length and baseline, you know how the depth is. Okay. All right, and so this is one option. Another option is called normalized cross correlations. Basically, it's the same thing, but this is more invariant to this type of method is more invariant to the lighting variations. Okay, so we talk about this in the template matching lectures. All right, so that's basically the core idea of stereo matching. Okay, steps from stereo. There's some, of course, it's not like it's one of the problems that's being kind of ancient in the field of computer vision. But still, because they're so important, people have been, over the past probably 30, 40 years, people are still working on this, okay? So I'm talking about why is that kind of still challenging, and there's still a room for improvement. So one thing that it's not so easy is because, first of all, the effective patch size is not that easy to change to select. For example, like if I only use if I want to find a patch, if I only use a small patch, okay, like a 3x3 patch, right, and I will be able to use a small patch, I will be able to find kind of very thin structure, right? Because it's very detailed. Okay, so you can see that you have a lot of thin structure you can find on the tree branches. Okay, so this is good. Can anyone tell me what's the problem of this? Like, what's the problem of this depth map? Yes, a lot of noise, right? And can you think about why is that the case? Like, why when you do the small patch size, then you suddenly get a lot of noisy estimates? Yeah, so the if you have smaller patch size, basically you don't have much information to describe a local regions. So when you do the scanning of the other positions, you could get something kind of, even though it's not a correspondence, but you still potentially get some very good match, and therefore you make the wrong decisions. Okay. On the other hand, if you have a large batch size, for example, in this case, you have a 20, like you have a global, you have a more context to describe a local regions. So you get less noisy results, like more accurate results, but because that you have a large regions, you won't be able to detect these kind of thin structures. Okay, so you can see that now it's get clean, but all of things are smoothed out. All right, so these are kind of fundamental trade-off that related to stereo matching. Okay, so this is just in words, small window, more detail, more noise, but large window, smoother disparity maps, but you have less details. All right, so there are a couple of kind of challenges here. For example, when you try to find a stereo matching, because when you try to find a stereo matching, you want to estimate depth. You want to estimate depth for every pixels. Okay, so imagine that you have a self-driving car application. You don't want to just say, "Oh, there are some region I don't know the depths," right? That would be dangerous, right? Because if some region you don't know the depths and you just bump into that a person or something like that, right? That becomes dangerous. So you want to be able to estimate everything. So there are some challenges, such as textureless regions, right? So imagine that if you take two pictures of this of me, then what you'll find is that uh, if you find let's say if you kind of want to look at these regions, like this logo, then you are able to find correspondence of the other image. Well, right? So that is distinct. But what if I try to kind of find a patch in the one image, and when I try to find the same patch via another image? It's really, really hard, right? Because this patch is matching to every other patches similarly. So these are textureless, right? They don't have kind of those information for you to establish a reliable matches. So you match everywhere. So in order to resolve this thing, you need to kind of understanding that, oh, these are probably similar depths than this guy, that you can have some depth boundary that you can estimate. So you have to use other clues, right? So this is hard. Another thing that could be hard is repetitions, right? So remember that when we talk about repetition, it's really hard when you try to do the kind of SIP feature matching, right? Same thing here, right? If you look at this this repetition, if you have a bounding box here, it matched to a lot of places on the right hand side. So the repetitions, it's really hard to get. Okay. Yet another thing is that when back in the module, the first module, we talk about that some objects, they reflect light differently, right? Some objects reflect light like in a diffuse manner, where kind of the color, the intensity of the surface does not change no matter where you look at them. But there are some regions, like any of the region, these things, they are highly specular. Which they reflect light in a particular directions. And so here's the example. You have a photo here. The photo is actually very refractive. Okay. In that case, the stereo, even though the stereo images are captured at slightly different viewpoints, right, of the same thing, slightly different viewpoints, some of the part will have highlight, right? And in that, when you have the kind of when you change viewpoint and suddenly the appearance change, and your stereo matching methods will struggle. So you can see that it's kind of mass, right? It doesn't really find the matches for that. Okay. So to resolve all this, there are probably kind of all these challenges. There are probably two types of kind of community have been deriving two types of approaches. Okay. The first type of approach is to use the is to use an optimization approach, right? So earlier when we talk about the kind of for each window you find the matches, but in that case, essentially for every single pixel in the left image, you try to find the corresponding kind of point in the right image, but all the decisions are independent for every single pixel locations. And this is why when you try to find, in this case, this classical benchmark data sets, when you try to find that window space based on each window, you will get something that's very noisy. Okay? So here's a it's noisy because you make decision like this pixel, the decision for this pixel and the decision for the pixel next to it, you make the decision independently. Okay, so that is bad because so that's bad because any kind of a slight slight difference in the matching, you get something that's kind of these kind of noise, right? So for some random pixel, you get matched to different locations. So can you think about what kind of constraint or what kind of regularization you can add here, right? How do you make the pixel not depending, not just independently make decisions? What type of constraint will make sense? What will be the typical depth map looks like? Like, so this is ground truth. Any idea? So what we want is that we want to make sure that we are not making depth estimation independently for each pixel, which means that nearby pixels should be depending on each other, right? We want to make sure that they depend on each other. But how do we make them depend on each other? What are the criterions we want to impose? Okay, so if you look at this test map, how do you describe this test map? Any thoughts? they obviously do not look like the left hand side, right? It's not very noisy at all. Anyone give me some ideas? Like the idea is that we want to get something kind of neighbor within a neighbor. What are the depth map value looks like? For nearby pixels, what will be the depth value looks like? Anyone? Yes.
Take a look at Gaussian blur, so set the depth of the pixel for like weighted average of like
Weighted average of nearby pixel. Yeah, that makes sense. But you're saying something like a post processing of this, right? That makes sense. Yeah. So, but here is like something that we want to kind of some property we want to enforce. Okay. So I think your idea makes a lot of sense. Like you want to go to that solutions. And here I want to understand is that what are the kind of prior knowledge about the depth map will look like without looking at the matchings, right? So this is something that we want to enforce. So if you look at the nearby pixels, overall nearby pixels, what are the depths that look like? What are the depths? What are the property of the depth map? If I kind of close your eye, if I randomly point at regions, neighboring pixels, what can you say about the depth map values of 2 pixels? Yes.
Are the same.
Yeah, they are going to be very similar, right? So this is similar to the when we talk about Lucas Canade, that there's some property that locally smooth. Like if they are the same object, they move together. Like similar here, that if they're like this is kind of it's probably the regularity of our world, right? Because object is the object is not every single pixel it's an object, right? It's a fundamental things about the world that things are basically locally. If you look at the depths, they are locally constant, right? You kind of look at this, like basically the chair table is here and locally similar. Okay, so if we know that this is kind of the prior knowledge that we know about our depth map. So what we could do is that we can come up with an objective function that can capture this knowledge, right? Okay, so here's the one way to do this. So I can cast the problem instead of trying to say, okay, every patch make decision by themselves. We can cast this as an objective optimization function, optimization problem, where I look at for image 1, for the patch from image 1, I basically try to find the disparity, like the shift disparity, such that the shifted window from image 2 is as small as possible. Okay, so this is basically I want to find the DI such that these guys are the smallest, right? This is the data term. Okay, but if you only have this data term, what will happen is that it will just give you something. It will just give you something very noisy because when you decide a patch is which patch match to this patch, is you're making decision independently. Okay, so what you could have add is one way to say this smoothest term. Okay, which means that whatever patch you have, if I have a patch locations, the solution. Okay, sorry. If a pixel, the estimated disparity is di, and if di and dj, the nearby pixels, the depth or the disparity should be similar. Okay, And what you do is that you add an optimization terms objective that make sure that they are similar. Okay. So this is I'm spending kind of move slowly here because this is so prevalent in computer vision. So basically, many of the computer vision problems, you want to estimate a grid of solutions. Either it's a segmentation, either it's a depth map, it's an optical flow. You can cast this in a similar way. So one thing is that you have some data term that you want to make sure that they match well, and also you have some regularization term. Okay, regularization term basically encode your knowledge about what the solution should look like. Okay, in this case, the solution should look like a smooth depth map. Okay. And once you write down the objective function, you can have some tools to solve it, right? So typically people solve this with some algorithm called GraphCut, okay? So here is the result look like the same matching, window-based matching, but you just get that it's much more accurate, right? So you can see this before this is the noisy results, and after is the results, right? It's become much more closer to the real things. Okay, so this is the power of optimization based approach, right? So you're simply adding some priors about the depth map, and instead of independently making decision for every single pixel, you jointly solve for every pixel together. Okay. All right. So, but of course, you can see that it's in probably 20 years ago, right? This is being very accurate, very good. But it's still ancient, right? So what happened in the past 20 years? So it's the rise of machine learning, right? So now, instead of trying to say, okay, I want to kind of human to come up with some objective function like this, try to come up with what does it mean to have a good match and what does it mean to have a regularization. Instead of try to have a human to write down the objective function, maybe we just collect data of real 2D kind of stereo pair as input, and I will have some ground truth depth map, and we just try to use a machine learning model to learn to predict this. Okay, so probably the past 20 years is all about that. All right, so try to replace, because here we need a human to design these objective functions, but there are some advanced methods to try to say, okay, should I use a different descriptor to describe these things? L2 maybe good or maybe not good. Maybe I need to use robust functions. And the smoothest term, you can also do some variations, right? But instead of having human in the loop to design this and solve this, you can just use a machine learning model. So the way you do this is that you collect data like input output pairs, and you can train the model, optimize the parameters of the model so that your prediction is as close to the target as possible. Okay, so here's one example of what this can do. Right? So here, there's no, it still has the kind of basic principle of this stereo matching. You still need to look at the scan line and to do the matching. But here, they are doing this matching in the deep neural network. Okay? But you can see that with this, you are able to get much more accurate results. Okay? So you can see that you don't need to have this trade-off between the small window size, large window size problem, right? So with just, you can actually detect these kind of same structures from a pair of images and also the large smooth area as well. Okay. So of course, like people you use start to when you encounter a problem, this is probably the go-to solution that you will use. Okay. right, questions so far about the stereo, depth from stereo. Okay, so let's quickly recap. So things to remember: epipolar geometry. There's some terminology that you probably want to remember. Epipoles are the intersection of baseline in image planes, and the matching point from in second image lies on the first line, first on the line, and passing it to its epipole. Fundamental matrix mass one point. If I give you a xy location of 1 point, fundamental matrix basically brings you to the line in the second image and the other way around. And you can solve for the fundamental matrix using matching pairs. Okay, right? And you can recover the rotation translations. All right, and then with this relative epipolar geometry, you are able to warp images into parallel lines. Then you can estimate the disparity by finding point, because the epipolar lines now is horizontal lines. And then you can find the correspondence in the just along the scan line, as opposed to find everywhere, right? And the depth is inverse to the disparity. All right, so that is the kind of summary of what we talked about last time. Questions so far? Okay. All right. If not, then I want to kind of motivate why we want to talk about the next one. All right. So far, when we talk about this module 3, we start with like how a 3D point is related to a 2D point. Then we talk about how you can use this to measure heights, to calibrate the camera, and then talk about two view cases, right? Two view cases means that you have images that are captured from rotating camera that give rise to image stitching problems. And then we just talked about is the images captured from translating cameras, then that gives rise to stereo matching. All right. So, but all these are single camera or two camera cases. But now what we really want is that what if I have multiple images get captured, like maybe I want to scan the objects, right? So how do I recover the three-dimensional structure from these images? Okay. So this is called the structure from motion problem. Okay. So basically the definition structure, it means here we means that there are some 3D points on the object surface that we can recover, right? So you can think about it's a 3D point cloud of the scene, and there's a motion that means that we have the camera location and orientation, right? Where the camera is and how they are oriented. Okay, so the idea of so you'll hear this term a lot in 3D computer visions. So we want to have this structure from motion problem, which is you get a 3D point cloud from moving camera, right? If you have a moving camera, then capture this, that's the thing. You want to be able to recover the 3D point cloud from the camera. Okay? So obviously, this is probably the holy grail of 3D computer visions. There are some applications. One application is, of course, scanning. Okay? So if you have this is basically have some airplane fly through the city, and you are able to recover the three-dimensional structure of the city by just images alone. You don't need an active sensor of like LiDAR to capture this. So here you can see that it captured all these details. Okay, so there are a lot of application. Obviously, you can do the. So instead of measuring, you can measure the you can do instructions. You can monitor cities development. You can do like those like inform policymaker to make decisions. You can do kind of if it is historical site, you can do preservations. Okay, so all these are kind of applications. Another application is the virtual tour. So people kind of, you want to sell a house, you want to buy a house, and you want to be able to see what's going on in the house. So this is the application, right? So if you do the 3D reconstructions, so that you can view this from like you want to know what the home looks like. Instead of getting there in person, what you could do is that you can have this kind of application. You can shop around here like this. Okay, so you can recover the whole home in 3D, so you know how things are related relative to the spatial layout looks like. And then you can, if you want, you can kind of hop onto one of the room and you can see what that looks like. Okay. All right. So other applications, for example, people have this kind of, you have some ancient artifacts that you want to preserve. One kind of important way is to preserve them digitally. Okay. So here's the, and then you can also do this for public display. Okay. So people, so in museum, they have a lot of like a 3D scanning kind of technology to scan and preserve, capture these details. Okay. Of course, you have a lot of application in the movie industry. So, for example, how do you actually? Where's the? There's no video. Okay, so basically, how you kind of, if you have a moving camera, you want to insert something 3D, some effects in 3D. Maybe in this case, is a hole that's virtual effects into your video feed. Then you need to know, the first thing you need to know is where the camera is, right? You need to know where the camera is so that when you insert any virtual content, it's going to look real. Okay. Right. Some other let's see. Okay, so here's a kind of examples of these virtual kind of insertions. So these are the key points that you will be able to recover, like 3D key points you're going to recover. And you also know the camera locations. And because of that, you are able to, this is the virtual object you inserted. But with that, you are able to kind of insert virtual objects. So here are some examples. All right, so see the breakdown. So all these are virtual things. You can add like reflections, spectacular, kind of make sure the color looks great, kind of add shadow and so on. But these are all just single frame, right? So how the question is, how do you make these things look real in the video, right? So this is kind of that powers probably the entire movie and kind of entertainment industry. How do you make them look real when you have a moving camera? And this is where the camera estimation really matter. Okay, you need to estimate the camera, where the camera is, so that you know how the object should appear in from your video viewpoint. Okay. All right. So just some more applications. There's just so many applications. So applications. This is one of the startup that you can people come up with. Basically, when you have an construction site or something that you want to kind of inspect, right? You want to inspect the house of the architectures or the buildings or some I don't know what this is, but basically it's hard for human to be there, right? But it's much easier if you have like drone to fly over the large scale in, structures like a bridge, under a bridge or something like that, to inspect whether the structural stability is still there. So with this, you can recover. If you can recover the 3D structures, you are able to use this and then kind of the engineer or the civil engineers will be able to inspect these things much easily. Okay. Of course, you can make things more realistic. So right now, if you go to Google Map, you you'll probably see that it's not just like a top-down only satellite view. For some places you can actually see them immersively. Okay, so here's some examples. You actually can see like they as if you're there. Okay, you can even change time and then kind of view this the whole things. Right. So this is the application of novel view synthesis. Okay. So myself, I also do some work in this domain where I imagine that you go on a hike. You go on a hike and you capture a bunch of videos, right? But what you really want is to be able to figure out how these videos and come up with a representation so that you can re-experience this hike, right? So you can actually have a smooth trajectory into like your experience. Okay. And with that, you can actually do the large scale, for example, campus tour. For example, if we scan the campus and we can put them online, and then other people can just have virtual tour to the campus. All right, so all of these applications, they have several main steps. Okay, the very first steps is this is the classical computer vision, 3D computer vision pipeline. Okay, so it starts with the following. All right, so you start with the images. So the idea is that I have multiple images, and I want to figure out what the 3D point inside these images and the camera orientations. So this is the problem called structure from motion, right? So now what I want to do is that usually what the next step is, like once you have these points, but these points are only come from the seed features, right? Which means that it's very sparse. But I want to make sure that I have a dense coverage. So what you can do is that you take the estimated camera poses, but you fix it, and then based on the camera pose and the 3D point cloud and the images as well, we figure out denser matches, right? And this is called multi-view stereo. It's basically the stereo algorithm we talked about so far, but with multiple images at the same time. So it's quite right. That's why it's called multi-view stereo. Okay. And the next is that you want to figure out the kind of the model, right? What is 3D model of this object is. So this is from all these points, you get the meshes. Okay, so if you want to choose the mesh representation, you have all these 3D points, and you can figure out a mesh of this. And then if you want to have the appearance of the things of the objects, you can do the texture mapping, right? You basically figure out what is the RGB and specular representation of that. Okay. So if you're all together, this corresponds to the so-called image-based modeling. Okay. So I want to do the 3D model, but I want to use the kind of 2D images to do the modeling. Okay. So what we want to talk about in terms of the actual techniques, first of all, we want to talk about a simple case for structure from motion. Okay. And this has very, very kind of nice, elegant algorithms behind that. Right. So the first things I want to describe is that you can solve structure from motion with just linear algebra. Okay. So this is when, but there's some assumption, right? The assumption is that if your object is, if your camera is further away from the object, okay? Basically, you have a turntable here, you have a camera here, you capture this object in multiple view, okay? So it's under the orthographic projection settings. When you have that assumption, you can simplify a lot of things, okay? So again, to remind you what orthographic projection is, it's not perspective projection. It's basically just you have an image you see, it just your 3D thing is just directly projected onto your camera. Okay, the camera, the image frame is that things. Okay, so under this simplified projection models, you can you can perform the structure for motion very easily. Okay, so here's how it does. So imagine that you have a camera, like this is a camera, and now you are not describing the camera in terms of the object center and then draw the lines. Now here the camera is that you only have this A1, A2 that is specified the orientation. If you have two vectors, that will specify the orientation of the camera, right? So you have the kind of coordinate frame here. Okay, that's called A1, A2. And imagine that if this X is described in this coordinate system, in the camera coordinate system, the projection here is super simple, right? The projection is just said, I just ignore Z. I don't care about Z. I just take the X and the Y. Okay, that's the projection model of the orthographic projection. Okay, but similar to the pinhole camera or perspective model case, that this X may not be described in this X right now is in the camera coordinate system, but we want to be able to model the 3D point in the wall coordinate system. Okay, so the way we do this is that we know that there is a rotation and translation between the wall coordinate system and the camera coordinate system. Okay, so you have this wall coordinate system x1, xy, z, and being rotated and translated, then you get the 3D point in the camera coordinate system, then you can do the projections. Okay? All right, so now we can simplify this a little bit. Like you have this, we can simplify this a little bit. For example, if you multiply these projection metrics with the R, you can call this RF. And so with that, it's become like this. Okay, the UFP, this is the 2D coordinate of the projected 3D points is the global 3D coordinate with the rotation and translations. Okay, so here you can think about the rotation here is basically the rotation here is basically that A1 and A2, right? The A1, A2 basically talks about how camera is rotated. Okay, so it looks like this. This is called affine projections. That this projection looks like this, right? You have an XYZ point in the 3D world, and based on this A1, these two vectors will get projected onto this image frame, and with some global, with some projection of the world origin. Okay, so this is the simplified projection models. Okay, so now the problem is the following. I give you a correspondence, 2D points in several frames, right? So I have a bunch of 2D frames that get tracked over time. I get you a bunch of different 2D positions over different viewpoints. Now the question is that we want to estimate the 3D points from these 2D points correspondence. I want to know what are the location in 3D. At the same time, I also want to know what are the parameters of this camera, how the camera moves. Okay, so that is the structure for motion problem. From the 2D position, 2D correspondence over time, you want to be able to figure out what the 3D position correspond, 3D points correspond to the 2D trajectory and the camera locations. All right. So the first step to solve this, the first step is that we find that it's kind of annoying to have this TXTY for all the kind of points. So, but fortunately, if you take the mean, if you take out the mean of this guy, and then if you take if if you take them, okay, for each frame, if you take all the points, if you subtract the mean, make them zero mean, it turns out it will get rid of this t. Okay, so you can actually compute this. If this guy, if you just plug this xi into these things, you'll find that it's the t, the translation will disappear. Okay, so this is just a simplifying steps. So if I work in the if I work with the normalized coordinate, I get something like this. Okay, you have a 3D point in the work coordinate system, and you get projected onto i's camera. J's point projected onto the i's camera. You get a 2D coordinate. Okay, so now what we have is we have a bunch of so you can think about, you have this matrix, right? You have this point, each point is being seen by m camera. Let's say you have 50 cameras, 50 camera capturing the same thing. So you have 50 cameras. So you have a 2m by 3, right? So each camera is 2 rows, right? The projection matrix. And at the same time, you have, let's say, 100 points. 130 points are on this. Okay? Right. So if I know the 3D points, and so the question is, if I know the 3D points of these things, and I know the camera projections, I will be able to figure out what are the projection points, right? I have a key point, I have a kind of projection matrix, then I can figure out what their 2D location is. Okay? So this forward process is easy. The question now is that, but we don't really know these guys, right? We don't really know the camera orientation. We don't know the 3D points. All we know is that we have a bunch of 2D points, and we can establish a correspondence across frame with Steve, with Lucas Canade, and so on. Okay? So what we know is these 2D metrics. So the structure from motion problem correspond to this, right? I have basically a big matrix of n points. So I have n points, different point. For each point, you have some measurements across different cameras. Okay, so think about this. Basically, it's a video. You can think about this as a video. I scan through this object, and then for each when I detect either Harris coordinate points or C features, I get to track that points across the different views, right? So I have this big matrix. So now the key is that how do I get from here to here, right? So this is the main problem. Any ideas how we can solve this? I have a big matrix, and I have I want to be able to factor. You can think about this. This matrix is coming from the camera. The kind of, you can think about this motion matrix and structure matrix, right? So I have motion and structure. They kind of get intertwined together through these multiplications to give me these 2D points positions. But now I want to go the other way. I want to be able to factorize them. Okay? So the way we can do this is the following. So we need to make some observation here, right? Even though we have a big matrix, maybe you have 100 points, maybe if I have 50 cameras, 50 frames, then I have 100 by 100 matrix. I have a big matrix, 100 by 100. But the question is, what's the rank of this big matrix? 100 by 100. What's the rank of this matrix D? Any thoughts? What's the metric rank look like? Would that be 100? Would that be a full rank matrix? Any idea? Well, this is going to be the key idea behind the methods. So suppose I have a 100 by 100 matrix. Like if I don't have any constraint, like the maximum rank is going to be 100, right? It's possible because 100 means that I have potentially 100 linearly independent column vectors to expand this space, right? So that's true. But I know here this matrix is coming from two matrices multiplied together. And this is the 100 by 3, and this is 3 by 100. Okay? So just look at this. If I have this matrix, what's the rank of a 100 by 3 matrix? What's the rank, the maximum rank they can have? Can it be 100? It cannot be 100, right? Because the maximum rank is going to be the dimensionality, the minimal dimensionality of this matrix, right? So because you only have 3 column here, so the maximum rank is 3 here. And same thing happens here. This thing, the maximum rank, the maximum spaces that they can span is 3 here. All right. So if I have a 3 matrix rank for 3, a matrix rank for 3, they multiply together, the matrix rank is still 3. Okay. So when I try to do this decomposition, because the measurement and the motion and this guy, the maximum rank is 3 only. So which means that the one way to decompose these things is the following: is to take, if I have this D matrix, if I take a SVD, I get to, this is still a 4 rank matrix. So what I can do is that once I figured out the SVD, I can take the top 3 eigenvalues only. So I enforce that they have matrix rank of 3. Okay? And then I can do the decomposition. I can split this thing, part of them into a motion matrix, part of them into the structural matrix. Okay? So this is the key idea. And next time we will continue to talk about how the full algorithm. Okay? All right, thanks.